Welcome back. In the previous classes, I was talking about the sliding mode control as well as sliding mode observers. In this class, I am going to discuss some kind of the implementation issue of the sliding mode controller as well as the observer, and that issue is basically called chattering. So, in this lecture, we are trying to understand that what is actually definition of chattering and how basically chattering can be minimized. So, that kind of things I am going to explore in this particular lecture. So, main purpose of the discussion, we are trying to understand first the advantage of sliding mode control, and obviously then I will come to the limitations. Basically I am going to explore the practical limitation. Okay. So, what we have seen so far, that sliding mode control is obviously one of the robust control technique, and that is applicable for both classes of system, linear as well as non-linear. Obviously, in presence of the plant parameter variation and disturbances, we are able to talk about insensitivity with respect to the matched perturbation, and due to that reason one can able to tell that sliding mode control is very less sensitive with respect to plant parameter and variation. We have also seen that whenever we are actually in sliding phase, because in sliding mode control we have two phase, and this is actually philosophy of classical sliding mode control. So, we are basically using discontinuous control. We first land up to the sliding surface, and after that we are going to maintain. So, during this phase our system order is going to reduce. Okay. And now you can able to design the feedback based on any existing control methodology, and somehow these two phases are decoupled, and that kind of advantage basically we are getting from the sliding mode control. After that, obviously in several practical application, operation is on off. Okay. Particularly if you take the example of power converter. Now power converter has several use in electrical vehicle, drones or several places. Okay. So, if you see the control action, that inherently on off in nature. So, sliding mode is basically quite suitable for that particular classes of system. In this particular course, already we have seen several applications that is related to robotics, electrical drives, process control as well as the motion control. So, what is conclusion so far? That sliding mode control is one of the powerful robust control technique, and which basically relies on the discontinuous control action. Now, let us come to the one of the obstacle of the sliding mode control implementation, that is so called chattering. So, first I am going to define the chattering. So, somehow chattering is not a desirable phenomena, and it is characterized as the oscillation with finite frequency as well as finite amplitude. And why basically this comes into picture? Because whenever we are constructing sliding surface or sliding mode control, at that time first step we are doing the modeling of the plant. Okay. And during this modeling we are somehow neglecting some part which has time constant that is very fast. After that, during the implementation, two subsystem also comes into picture. This side we have actuator, this side we have sensor. Okay. So, these two subsystems has also some kind of dynamics. Okay. And basically we are never caring about that dynamics during the design of the sliding mode control, and due to that reason these two dynamics is going to create the obstacle during the implementation, that I am going to explore in this lecture. Second obstacle is the discrete time implementation. If you see the current hardware scenario, most of the hardware, either microprocessor or computers, that actually accept digital signal, okay, also generate the digital signal, and somehow since our design is based on continuous time philosophy, whenever we are discretizing, then somehow we lose something. So, how basically this is going to impact on our system? So, our accuracy, control accuracy is low, and if we have mechanical actuator, it is possible to show some kind of wearing and tearing inside mechanical actuator. And now we have already seen that robotic is one of the current era, and in that particular robotic system, that is fall in electromechanical class of system. So somehow these kind of strategy create some issue like chattering if you are going to implement the classical sliding mode control, first order sliding mode control, that is actually developed by the Utkins and their subgroup. Now what is key point? Chattering is harmful phenomena caused by the unmoduled dynamics and discrete time implementation. Okay. So if you see carefully, then sliding mode control don't have any problem. Okay. What basically we are doing, since in order to design sliding mode control, we are neglecting, so that neglection basically going to create problem. So now another question, how to incorporate that such that one can able to minimize. So that we are going to look into the next chapter. Now let us try to see the challenges of chattering. So I have already told you that some system which is inherently need on-off kind of control. So now on-off control is required. So I cannot able to tell that okay, everywhere I can replace on-off control by some kind of continuous control. Okay, because operation is based on the on-off control. So only thing I can able to do, switching frequency I have to control in such a way such that I can able to minimize the chattering. So in literature, several methodology has been proposed by Lee and Utkin, and after that in next module we are also going to see that higher order sliding mode control. Okay. So somehow that methodology comes into picture due to somehow minimize this effect that is called chattering. So what is key point? Chattering poses significant challenges, especially in power electronics, where switching frequency must be carefully controlled. So chattering with unmoduled dynamics, because I have already told you that one source of chattering is unmoduled dynamics. And what is source of chattering? Actuator. And during the complete control system, we need sensor, data processor, several things are required. And every subsystem has some kind of a small time constant, and during a steady state somehow we are ignoring this. But due to the nature of the on-off control with high frequency, these dynamics may be perturbed. Okay, and that will cause the sufficient degradation of the performance. Okay. So in order to understand the effect of unmoduled dynamics on chattering, what I am going to do? I am going to take a linear system, and here in this system, what is omega? Since in order to implement some kind of control, so this is the plant equation. After that I need actuator. So omega is nothing but the input of the plant and somehow output of the actuator, and control I am going to apply here. So control, basically control logic we have designed, and through hardware that is called actuator we are going to implement. So somehow whatever output of hardware that can of signal, somehow this plant is going to receive. So that I have represented like this. Here sigma, that is called sliding surface, that is the linear combination of all state. Now what is key point here? Unmoduled dynamics from actuator can lead to chattering in sliding mode control. That we are going to verify. So this is the block diagram. I have plant. This unmoduled dynamics is nothing but the actuator, and here I have control logic. So based on logic we have designed some kind of control action. Now you can see here that this omega and u are not exactly the same. So whatever control we have designed, same control is not implementable here. Why? Because this actuator has some kind of dynamics. So now we are going to see their effect after designing the sliding mode control. it is possible to show that if system is linear, then this block is almost equivalent to this block. What you can do? Now you can put the unmoduled dynamics on the right side of the plant. Okay, again this unmoduled dynamics, you can see here that whatever control I have designed, that is exactly applicable to plant. But now what is difficulty? That output of the plant now that is somehow modified by this unmoduled dynamics, and our sliding philosophy is based on sigma star. So somehow linear system, these two are equivalent. You can also think like this: I have plant, so this dynamics correspond to the sensors unmoduled dynamics, this correspond to the actuator unmoduled dynamics. Okay, so somehow both are the unmoduled dynamics only, but for the theoretical analysis point of view, one can able to see the effect of the sliding mode control here very easily, and obviously after once I will do analysis, same kind of analysis I am going to perform here. So here you can see that in equivalent system, this system I am telling that is equivalent to this. So in this equivalent system, now sliding mode control I can able to design, and due to that design, in place of W now I have replaced the omega, because in this upper block diagram, A block diagram, you can see that input to plant is omega, and due to that reason we have written equation like this. But in equivalent plant, now input is U, and due to that reason we have written equation like this. But how basically this equation is different from this equation? You can see that in place of sigma, now I have to apply sigma star. Why? Because output is sigma star. Now what I am going to do, you can see here that sigma and sigma star, and here just I am going to utilize the information of sign. So somehow if sigma and sigma star are very close to each other, it means that if they will not change the sign, then I can able to get exact sliding. Okay, so somehow equivalent representation tells us that how to get exact sliding in case of the unmoduled dynamics. Okay, now I have to understand the impact. So unmoduled dynamics can cause high frequency oscillation. So now this high frequency oscillation I have to characterize. So I am going to characterize this. I have already told you that this chattering is very dangerous whenever our actuator is mechanical, because if our actuator will switch with very high speed, then that will create wearing and tearing, and somehow heat is generated. Okay, that will cause some kind of difficulty, and due to that reason proper selection of gain is required. And if you neglect unmoduled dynamics, sometime you can also able to see the instability. So this is the key point: unmoduled dynamics introduce chattering, which must be addressed through proper gain selection. It is possible to show that if you design M is the gain of the sliding mode controller, and if you also account the unmoduled dynamics, you can able to reduce the chattering. Now, so up to now we have discussed that what is effect of actuator and sensor with a small time constant, and what was our observation, that if we have just sensor and somehow if output sigma is approximately equal to sigma star, then exact sliding I can able to achieve in presence of unmoduled dynamics also. Okay, and now it is possible to show that gain of the sliding mode controller is very crucial to reduce the chattering. Okay, and that somehow theoretically we have to establish that how basically gain is related to the chattering magnitude, and obviously design is required, because if I am able to establish that gain is responsible for the chattering magnitude, then I can able to reduce the gain. Obviously reducing gain is not possible always. Why? Because magnitude of that gain should be greater than the all kind of uncertainty. So only one approach is there. What you can do, try to rely on the feed forward control. So designing feed forward control, it is possible to show that some kind of known part we are able to cancel, and in this way I can able to minimize the level of gain. Now let us first try to see the equivalent structure. In equivalent structure, what we have done, again please come back to the representation. So here I am going to take this system, okay, and here sigma is the input to the unmoduled dynamics, and I am going to assume that unmoduled dynamics is represented by second order dynamics, okay, and where time constant is very small. So sigma is the input to the unmoduled dynamics, and sigma star is actually input to the controller. So same kind of things I have written in the mathematical language here. So I am considering the unmoduled dynamics which we have neglected. Why we are neglecting? You can see from here that if you are going to put mu equal to 0, mu is very small, then effect of these first two terms z dot and z double dot, that will disappear, and z equal to r sigma, okay. Now here sigma and sigma star both are not same, so sigma star is some kind of value, so z is the output of the unmoduled dynamics. So here unmoduled dynamics I have, so sigma is the input, and after that what is output? Output is z, and after that whatever things I will pass through this, this is somehow some kind of gain, that is q, and after that from this I will get sigma star, and this sigma star, based on this sigma star I am going to design this sliding mode control, okay. Now what I am going to do? I am going to do a state space representation of this system. So how to do a state space representation? So you can define z1 equal to z, and after that mu z1 dot I am going to define as a z2. So if you take mu z1 double dot, that is nothing but mu squared z double dot, then I will get this dynamics, okay. So basically unmoduled dynamics are represented as second order system with a small parameter mu. These are the small parameter. So for this system I can able to apply the theory that is called singular perturbation theory. And what singular perturbation theory is suggesting, that if this their derivative sigma dot is also bounded, then I can able to substitute mu, that is very small. So mu z1 dot, since mu is a small and due to that reason z2 dot approximated by 0, and similarly this right hand side of the last differential equation that is also approximated as a 0. So basically this is already 0 dz2, so only I have choice that r sigma that equal to z1 approximated by, I have to write, okay, and some more term will appear here because that is just a approximation. So same kind of things I have written here, that after applying this singular perturbation theory, what happens? After a finite time, once transient is over, it is possible to show that z1 is going to converge here, okay, where sigma 1 is the accuracy, and if mu is very small, if mu tending towards 0, then z1 is exactly equal to r sigma. And what is sigma dot? That is q into z, and z is equal to z1. So if I substitute, now you can see here that q and into r, that equal to sigma, and some small term comes into picture. So as mu tending towards 0, now what is our observation? Sigma star is exactly equal to sigma, okay. So exact sliding I can able to see in the vicinity of this particular bond. Why? Because always some kind of, so these two, actually I am using sine of sigma star equal to sine of sigma, okay. So everything is actually depending on the perturbation parameter, that is function of mu and t, and due to that reason I am telling that I will get sliding mode kind of behavior in this vicinity, that is the physical interpretation. And if mu tending towards 0, so there is no unmoduled dynamics, so what happens? I will actually exactly see the sliding mode in with respect to sigma equal to 0. Now I have already analyzed the equivalent system, okay. What is equivalent system? Let us come back again. This is the equivalent system, okay. Now I am going to analyze this original system. So what is our observation for the equivalent system? if mu is not very small, then exact sliding I cannot able to achieve. In vicinity of some kind of epsilon mu, I will get the sliding, and this vicinity is responsible for the chattering. Okay. Now I will take original one, and we are going to analyze stability in this vicinity, and that confirm the chattering. Okay. So by analyzing the below dynamics, I can able to give result for the A1 dynamics. This is A and this is B. Okay. So let us now see the mathematical model of that system. So here in this system, in this representation, actuator will get the input from the sliding mode control, and after that whatever input here, now plant is going to get input omega. So same kind of things I have written. U is the input to the unmoduled dynamics and omega is the input to the plant. Again I will do the state space representation. You can see here state space representation is a little bit different because I do not want to apply the singular perturbation theory. Okay, now I am going to do Lyapunov stability theory. Okay, so how to do stability? I have three state variable here. So I have first defined sigma 1 equal to sigma, that is sliding variable. After that what I am going to do? I am going to select CB, eigenvalue of CB equal to identity. I have select sliding mode in such a way such that this will preserve. It is possible to show always these kind of assumptions are satisfied. After that what I have done? You can see here that I have calculated the derivative, first derivative sigma dot, and sigma is nothing but C into x. Okay, so what is sigma dot? Cx dot, and what is x dot? That is nothing but Ax plus Cb into W, and Cb is unity by design, and due to that reason W will appear here. Okay, W is nothing but the input to the plant, and we have seen here W is Q into Z. Now I am going to take one more derivative, and if you take one more derivative, then what happens? Now after taking one more derivative, here Cax dot comes into picture. Okay, and W dot comes into picture. What is W dot? W dot is nothing but the Q into Z dot, because Q is some kind of matrix, constant matrix. Now I know that here Z1 dot equal to Z2 from this particular expression. So due to that reason here this term comes into picture. Similarly, if you calculate sigma 3 dot, then control explicitly appear. Whatever nonlinear term I am going to keep here. Okay. Now it means that our unmoduled dynamics is represented by this expression, third order equation, sigma 1 dot equal to sigma 2 dot equal to sigma 3, and sigma 3 dot like this. Okay. So now I am going to construct Lyapunov like function. This is not exactly Lyapunov function. Why? Lyapunov function should be positive definite. So for all sigma that is greater than 0, when sigma not equal to 0, and that is only equal to 0 at the sigma equal to 0. But this condition is not satisfied. Okay. So due to that reason I am telling this is Lyapunov like function. Now V dot if I will calculate, and if I design M is larger than this whole value, then it is possible to show that V dot is less than 0. Okay. V dot is less than 0. Okay. And here we are also assuming one more thing, that if M is very high, then I can able to get sliding. Okay. What kind of sliding I will get? In this way all possible variables sigma 1, sigma 2, sigma 3 all equal to 0. Okay. And that is nothing but all higher order derivative equal to 0. So basically equivalent value, because whenever I am in sliding phase, I have already told you that one equivalent control X comes into picture. That is the actually confirmed by the Utkin's philosophy. Okay. So basically Z is nothing but R into U equivalent during the sliding. Okay. So same kind of things basically I have written here. Since I have some kind of uncertainty, and due to that reason in vicinity I can able to see this expression. Okay. So I have to select gain that is larger than Q into Z1. Okay. So in this way you can see that since what I have seen that V is sign indefinite, but Vx is less than 0. Okay. And where this kind of things is conformed in some vicinity, and due to that reason this system is attractive but not stable. Okay, what does it mean? That all trajectory will converge to some vicinity, and after that they can actually diverge inside this. Okay, so all trajectory is attracted towards this. Okay, but we lose stability, and due to that reason chattering is confirmed. In this way you can able to show theoretically that chattering is there. Now what is our next goal? Our prime goal to calculate the amplitude and frequency of the chattering, because that is finite. So for that again I am going to apply on off control. You can free to select any system. So I have selected here, you can see that nth order system and with only one control input for simplicity, and this is sliding surface. It is possible to show that how to realize sliding. So for that you have to take the derivative. Now once you are going to apply the on off control, so it is possible to show that in a steady state this and this are approximately constant, this and this approximately constant, and due to that reason whole plant I can able to approximate by this plant x dot equal to a plus bu, where a and b are the constant, and due to that reason, so in order to analyze the chattering, even if these two are uncertain, I can able to approximate that by constant one. So these are our plant, this is the sensor dynamics. Okay, now I am assuming that since I have equivalent kind of circuit, so h z equal to not x star. Okay, so whenever we are actually tuning the sensor, so we are adding one extra block. Why? Because somehow we want that in a steady state z will approximated by x star. Okay, so by designing or tuning the sensor for a specific application, that is very much essential. Now we are going to design sliding mode control based on the information of x star, and due to that reason now you can see that sliding surface is designed based on sigma star equal to cx star. Okay, this is the actually dynamics of the sensor. So sensor dynamics, I am assuming that here sensor is represented by just first order dynamics for the simplicity. We are assuming that whatever sensor that is stable, so how to make a stable? A matrix you can make it stable. Okay, now I have already assumed that whenever high frequency chattering occur, at that time system parameter become constant or approximated by constant, and u is actually sliding mode control at that time is sigma star. Okay, whatever output that came from the sensor, that pass through this gain user has to design. Okay, and in a steady state user has to confirm this. Okay, then I can able to actually show that x star or whatever sliding, real sliding or actual sliding, both are the same. That is the philosophy. So now you can see that in a steady state rate of change is going to cease. So at that time basically I have az equal to b into x. Okay, so at that particular moment I can able to show that, since what I have to do, I have to show x star equal to h. I know that x star equal to hz, and due to that reason I will calculate z from here. So z is a inverse b into x. Now I am going to substitute here, z I am going to substitute here, and now you can see here that I will get this expression. So this expression tells us how you can able to tune your sensor such that x is approximated by x star. Okay, so if I keep identity, then this problem is solved. Okay, so a static mode controller perception of the state should be aligned with the state to avoid the distortion. Okay, so these kind of tuning you have to do whenever you are doing the practical implementation. Now whenever I am applying the chattering phenomena, high switching phenomena, we have seen that system is approximated by linear system. Okay, with some kind of uncertainty. So I can able to apply Laplace transform. Okay, and I want to characterize the harmonic function, what kind of actually finite frequency or finite amplitude variation comes into picture, and due to that reason solution I have to express in terms of harmonic. So for that I am going to utilize the combination of Fourier series and Laplace series in the next part of this slide. Okay, so what I am going to do now, I have sliding surface sigma x star, that is C into x star. Okay. So what I am going to do? I am going to apply the Laplace transform both side. So this is the Laplace transform of sigma star t. So sigma star t is the our sliding surface. Okay. So I have either you can represent, because this is just function of x, due to that reason I have written, but obviously x star is also function of t, and due to that reason people are writing like this. So please do not confuse. Okay. Now you can see here that x star is nothing but h z. Okay. And what is z? If you see carefully here, that z is nothing but x star h into z, and z I can able to calculate from the sensor dynamics. So you can take Laplace transform here, and after that you can substitute here, and after that substitution you can able to get u basically we are going to apply to the plant. Okay. And what is the equation of the plant? X dot equal to a plus b into u. Okay. Again you can take the Laplace transform, then you will get this kind of expression. Okay. So please do by yourself. Now what I am going to do? I am going to show you the solution of this sigma, because why I am taking Laplace transform, finally I have to show that what is expression of sigma t. So I am assuming this is the solution. Now I have to calculate alpha and beta, then exactly I can able to understand the solution, harmonic solution. Okay. So after that control I am going to design. What kind of control I am going to apply? I am assuming that there is no distortion, because I have designed H such that there is no distortion. Then I can able to design u star equal to m signum sigma. Again these their component I am going to calculate. How to calculate this component? So for that one can able to apply the Fourier series analysis. Okay. So Fourier, this is the formula of Fourier series. If you substitute this whole quantity here and take integral, you can able to get this expression. Okay. So this work you have to do. Okay. Now what I am going to do? I know the expression of u star, I know the expression of sigma star. So I will take Laplace transform of sigma star and u star. So Laplace transform of sin omega t comes into picture. Here again sin omega t comes into picture, and after that I am going to substitute here. So that kind of things basically we have done. We are also assuming that mu equal to 0. Okay. Time constant is very small, because we are, whenever chattering comes into picture, once we are during the sliding, so already system is in some kind of a steady state. Okay. So that during that I am assuming that mu equal to 0. Okay. Now after taking the Laplace transform of this, I have this, and right hand side is this. Okay. You can see here that I have already tuned the gain of the sensor such a way such that these all three parameters equal to identity. So what is our conclusion now? I have to match left side to right side. How to match? It means that this term should not present. Okay. So when this term will not present, because this term, if you do partial fraction, then I can able to generate this kind of term, but I have to remove this term. Okay. And you can see that physically I will get this as a equivalent control. Okay. So in sliding mode control, since sigma equal to Cs and sigma dot equal to Ca plus Cb u, so how to calculate equivalent control? You can put sigma dot equal to 0. So u equivalent is nothing but Ca by Cb. Okay. So same kind of things actually came here. This is by designing the sensor gain, I can able to tune it. Now you can see here that since I know u0, so I am going to substitute u0 inside this expression, and then I can able to write the expression of u1 star, because they are high means finite frequency oscillation comes into picture, and due to that reason I have calculated u1, and after that I am going to substitute whole control inside this system. So if you see the system dynamics, now you can see that one frequency omega comes into picture and m is here. So due to that reason, chattering amplitude is depending on m, and how to actually mitigate the chattering, how to reduce the chattering, I have to somehow select this m properly. Okay. Now I have to see also frequency. So how to see the frequency? Again I will come to this expression, and in this particular expression what I am going to do, I am going to neglect this, I am going to neglect all initial condition because I have to calculate the transfer function, and after that I am going to look into argument. Okay. So, you can see here that one term, here term should be Js into I, but instead of that what happens, I have J mu into omega and I comes into picture. So, this is responsible for some kind of P or Si, you can tell. P, S I am not using because in sliding variable I am representing like this. It means that now omega star comes into picture and mu into omega. And what is omega? So, omega is nothing but here in place of omega star, you can also able to write here basically nothing but omega star. So, omega is omega star by mu. So, if mu is small, then you can see that frequency is very high. Okay. If time constant of the sensor is very small, then chattering amplitude is higher. That is the conclusion. So, in this way I can able to characterize the chattering, and how to reduce, obviously I have to control the gain. That is only way to actually reduce the chattering. That is the conclusion. So, now it is time to conclude this lecture. So, whenever we are designing sliding mode control, so at that time we have to tune sensors. Okay, we have just taken here sensor dynamics because actuator dynamics we have already considered, and sensor, after that effect of sensor I am going to understand. So, I have to actually I have to decrease suitably, and how to decrease it. So, we are going to see in the next part of this course, that how to properly reduce the chattering. So, for that several methodology is there. So, next 2 class I am going to discuss about that, and after that next part of this course I am going to talk about higher order sliding mode to mitigate this kind of phenomena. So, with this remark I am going to end this class. Thank you very much.